This video explains some of the basic concepts of curve fitting for laboratory assays. Laboratory tests are used to measure a substance from humans, animals, or plants. Some tests, for example, measure a protein in human blood. They usually produce a color or light. The color intensity can be compared with the test result of a sample of known concentration, called a calibrator or standard. In this example, the measurement has a similar color to a standard with value of 3, so the concentration in this sample will be around 3. To also obtain accurate intermediate values between the calibrators, the color measurements are fitted to a mathematical function in a process called curve fitting. In this example, 5 standards are shown, with known concentration values of 1 to 5. These values are plotted on the x-axis of the graph. The output signals ranging from 2 to 6 are plotted on the y-axis. In this example, the data points are fitted to a linear function. The fitted curve data points for the standards are calculated. In this case, they are identical to the measured signals. For each point, the squared difference between the fitted signal and the measured signals is calculated. The sum of these squared differences is called the sum of squares, and this is used to optimize the curve. If we change parameter a, the intercept, to 2, the fitted line moves up. The difference of the fitted compared to the measured signal is 1, and the squared difference is also 1. In this case, the sum of squares is 5. If we change the slope, parameter b, to a value of 2, the steepness of the line changes. The squared difference of the first data point is still 1. The second data point, however, differs 2 from the observed, and the squared difference is 4. The further the curve deviates from the actual measurement, the more the squared difference is. The sum of squares in this example is 55, which is a high number. The unknown sample measurement is 3.5. Since we have now optimized the 2 parameters for the fitted line, we can calculate the value of the sample. A signal of 3.5 calculates back to a concentration of 2.5. In this example, the data points are on a perfect straight line, however in reality this will almost never happen. Suppose one of the standards measures a little higher. The minimization of the sum of squares is then performed by testing many different parameter a and b values. This results in a line as closest to all the data points as possible. Now there is a difference between the measured value of standard 1 and the calculated value from the fitted curve. Based on this curve, our unknown value of 3.5 will also obtain a different calculated concentration. If you want the fitted line to be closer to a particular point or points, you can increase the weight value of these points. We will set the weight of standard 1 to 10. The squared difference will then be multiplied by 10. A deviation of this point from the line will have a 10-fold higher effect on the sum of squares optimization. This will result in a fitted line, which is closer to the point with more weight. Setting weights is a good way to increase the importance of the low-dose calibrators. Very often, the standard results do not seem to be on a straight line. Fitting the points to a linear function will show a substantial deviation of some data points from the curve. In this case, a non-linear fit function is a better option. Non-linear fit functions have more than 2 parameters, in this case 4. That's why it is called a 4-parameter logistic function. Fitting the curve to this function provides a better alignment with the data points. Optimization starts with start values. These should be close to the final parameter value. One start value is the maximal signal, and 1 is the minimal signal. The 4 parameters are optimized in the same way as fitting to a straight line. Changing the value of parameter A and parameter B, change the height of the fitted curve. The change of the four parameters, as is done here, with the feedback of the sum of squares, is essentially what the optimization algorithm does. The optimization of the parameters is a complicated process, and this is what is called curve fitting. AssayFit Pro performs both the curve fitting and calculation of unknown values. In the next videos, we will explain more in detail how AssayFit Pro can be used.